Okay,
Start.
so
Okay. Hi, everybody. Today, we are very glad that we invite Dr. Naoyuki Kanda from Microsoft to introduce his work in the joint modeling for the multi-speaker speech recognition, diarization, and separation. So, Naoyuki is my colleague, and we have been colleagues for like around a year, although a large ratio of it is actually remote collaboration, but still, Naoki also my good friend and the teacher to me in many aspects. So I will briefly introduce him by reading his bio, and I will hand it over to Naoki for his talk today. Naoyuki Kanda is a principal researcher at Microsoft Research in Redmond, Washington. His research interests include automatic speech recognition and a wide range of spoken language technologies such as speaker diarization, spoken dialogue system, and spoken document retrieval systems. His algorithms and system for far-field multi-talker conversation ASR won the first prize at IWSLT English Evaluation Campaign in 2014, and the second prize at the Chime 5 Speech Recognition Competition in 2018. He received a Bachelor in Engineering, Master in Informatics, and a PhD in Informatics from Kyoto University, Japan in 2004, 6, and 14, respectively. From 2006 to 2019, he served with Hitachi Ltd. In Tokyo, Japan, and held appointment as research experts and cooperative visiting researchers at the National Institute of Information and Communication Technology in Kyoto, Japan. He is a member of Institute of IEEE and Acoustical Society of Japan, the Japan Society of Artificial Intelligence, and the Information Processing Society of Japan. Okay, now Naoki, I'm going to hand over to you. You can start your presentation. Let's welcome Naoki.
Thank you, Joe, for introductions, and thank you, Sanjay, for inviting me to this presentation. It's a great honor for me to have a chance to present my research work for you. So today I want to talk about a joint modeling approach for rich transcriptions. And this is essentially the great collaboration with my past and current colleagues. I'm so grateful these colleagues in Microsoft, Hitachi, and Shinji in Johns Hopkins University. So, sorry, I am using the pointer mode and it looks like, okay. So maybe I need to stop presentation mode. So yeah, so the motivation today is rich transcriptions. The input is much speakers audio recorded by sometimes a single microphone and sometimes with multiple microphone. And also sometimes we apply speaker profiles as optional input that represents the speaker characteristics of participants. And the output is firstly the transcriptions, what they are speaking, and also we try to estimate who is speaking. So this is the task that I wanted to talk today. Rich transcription has a long research history. So for example, in early 2000s, there is international efforts like next to rich transcriptions or meeting projects. Also, there are recent challenges related to rich transcription, such as Chime 5, 6, or Die-Hard 1, 2. And during this period, there have been a great progress in the technologies related to rich transcription, such as speech separation, speech recognition, speaker diarization, or sometimes rich transcription requires automatic punctuation or capitalization, or sometimes it also tries to estimate emotions. Today, my talk is focusing on these three board techniques: speech separation, speech recognition, and speaker diarization and identification, because these three modules, the main is the center of the motivation of rich transcriptions. So how we can realize rich transcription by combining these techniques. So let's see one example. This is a meeting transcription system developed by Microsoft. Firstly, you can find microphone array here. This microphone array has 7-channel input. And we firstly apply daily reverberation, and after that, we apply speech separation. The task of this speech separation is converting the input from microphone array into 2 streams of non-overlap speech. So after speech separation, speech is non-overlap, so we can apply ASR systems. And after getting the ASR transcriptions, we apply diarization systems. And finally, we combine the result from 2 streams to get the final speaker attributed transcriptions. So the order of modules is separations, recursion, and diarizations. So this is what we are doing in Microsoft. But if we look at another system, we can find different architectures. So this is another example that I took from Time 6. This is STC system that won the Time 6 challenge. So what they did is, firstly, they applied diarization system called Target-Speaker VAD. And after that, they apply speech separation. And finally, they apply speech recognition. So the order of applications is different from what Microsoft is doing. They firstly apply diarizations and separation and recognition. So what is happening here? So these 2 systems can be seen as a modular system that is a combination of existing technologies. There are 2 things that we need to care about if we think about modular system. Firstly, each module is created independently. For example, if we look at speech separation module, usually speech separation module is trained by using the signal processing-based criterions. But that signal level criterion is not necessary to be optimal for automatic speech recognition. So each module is trained independently, and it's not directed to the final objective. This is the one issue that we need to care about when we think about modular system. One more thing that we need to care about is the mutual dependency each modules. For example, if we firstly know the speaker, like firstly apply speaker diarization, we can use speaker information to improve the speech recognition. We know that this is a speak adaptation. But on the other hand, if we know the transcription beforehand, we may be able to use that transcription, for example, to find where is the boundary of speakers just by looking at the word sequences. So there is a mutual dependency between speaker recognition and speech recognition. So if we use modular approach, it is difficult to use that mutual dependency. So what I want to introduce is how we can jointly model the rich transcription program. The motivation is improving the accuracy by using mutual dependency among modules or by optimizing the model towards the final objective criterion. Okay, so we have various components, but let's start from the simplest one, speech separation and ASR. We want to combine speech separation and ASR. The idea is super simple because we can represent speech separation and ASR by using neural networks. We can just combine speech separation and ASR, and we can train whole entire networks by using the ASR criterion. And that's it, actually. But there are 2 major approaches for speech separation and ASR. The one is permutation invariant learning. In this PIT architecture, we have multiple output branches as the 2 transcribe multiple speaker speech. The thing here is that we have multiple branch, but we don't know which branch corresponds to the first speaker and which branch corresponds to the second speaker. So what we do in permutation invariant learning is we calculate the all possible combination among this output branch and reference labels and use the best loss when we update the neural networks. There are two things that we need to know as a limitation of permutation invariant learning. Firstly, number of recognizable speakers are limited by the number of output. For example, if we have only two output, we cannot output three simultaneous hypotheses. This is architecture limitations of PIT. One more thing that we need to care about is the trying cost is order of factorial of number of output, because we calculate all possible combinations among output branch and reference labels. So this is the one major way of handling multiple speakers by combining speech separation and ASR. One more major approach is so-called speaker beam or Target-Speaker ASR. In Target-Speaker ASR, we feed the target bias into the network. The task is to transcribe only target speaker's speech by ignoring other speaker speech. A good thing of target speaker ASR is that if we can prepare the correct speaker profiles, maybe it's better. So if we can prepare the correct speaker embeddings, we can theoretically recognize any number of speakers. So this is a good thing of target speaker ASR. In 2018, Hitachi and JQ participated in Chain 5 as a joint team. And at that time, we need to cope with the four-speaker speech. By comparing these things, we selected Target-Speaker ASR as our architecture. So let's see our final architecture for Chain 5. So as an example of Target-Speaker ASR. So this is the architecture. In the bottom, you can find the input, and the output is a phoneme target. That is the whole network is trained by using ASR criterion. Here is the I vectors, and this I vector is used to identify who is the target speaker. And here you can see that there is an N-channel input branch. In Chain 5, we have microphone array. We are using microphone array. So the input is 4 channel of audio. So we feed that 4 channel audio directly into the network. So this part can be seen as joint training of speech separation and acoustic models. One unique thing of our acoustic model is that we have another input channel, so-called single channel input branch. The idea here is that we still wanted to use the signal processing-based speech separation modules. And we saw that the combination of signal processing module and neural network-based speech separation module will be best. So this input branch is used to inject the result enhancer signal from signal processing-based speech separation module. What we did in training is we firstly trained the network only by using the single channel input branch. And after finishing the training, we add N-channel input branch. This is a kind of speech separations. And we just updated these parameters in the second round of training. So here is the result. This is a word rate on Chain 5 dataset. Left-hand side is with the result without multi-channel input, and right-hand side is with multi-channel input. And blue is the when we input the raw audio. Orange is with daily liberation method, and finally gray is the result with our best signal processing-based speech separation module that we had in at the time of Chain 5. So you can see that adding multi-channel input is even effective than the best speech separation module that we have at the time of try 5. But the combination with the signal processing based speech separation was the best in finally. So this is the results that we got in try 5. Unfortunately, we got second prize at the time with this acoustic model. Okay, so so far we see the Target-Speaker ASR, and this is the again comparison slide with permutation invariant learning and Target-Speaker ASR. One more thing that I want to introduce today is the hidden comparison, and one more hidden comparison between the difference between permutation invariant learning and Target-Speaker ASR. So in the training of PIT, permutation invariant learning, we utilize all speakers' information in training. So, but on the other hand, when we think about target speaker SR, we usually use only target speakers transcriptions, although there is interference speaker speech, and although we know the transcriptions of interference speaker speech. So we thought that it could be a loss in the time of training. So what we propose in InterSpeech 2019 is a very simple idea. So we are still targeting the target speaker ASR. So here is the embeddings of target speakers. But usually we only have the target speakers out of the branch, but we add interference speakers out of the branch. And we try to maximize the target speaker's ASR accuracy and the interference speaker's accuracy simultaneously. The motivation is that by using the interference speaker's reference as the training target, we could be able to get the better representations for speaker separations. So this is the first advantage that we aim at. One more side effect, good side effect of this approach is that we can actually do the interference speakers SR by feeding the target speaker embeddings. It is a bit tricky, but it is interesting if we see the result. So this is the second side effect of this architecture. Here is we evaluated this architecture by using the simulation of LibriSpeech, simulation by using LibriSpeech dataset. So here is the tables that compare the clean acoustic models and target speaker acoustic model without auxiliary loss, and target speaker acoustic model with auxiliary loss. Maybe we can just see the average result. Here we use the two-speaker mixed speech as a test date. So if we use clean acoustic models, the result is super bad. Target speaker SR produced a pretty good result for this two-speaker mixed speech. And by adding auxiliary loss, we got further improvement. So this is the effect by adding auxiliary loss. One more table is that to show we can do interference speaker SR. So what we did here is that we feed target speaker embeddings, but try to estimate the interference speaker speech. So if we compare the target speaker SR result, there is a slight degradation of accuracy, but it is still working. I will use this this property soon in the next topics. So I would like to introduce it here. Okay, so far we see the speech separation and ASR. So then here is one of the highlights of my today's presentations. I want to combine speaker diarization into consideration. So fundamental question here is, can we formulate the joint procedure of ASR and speaker diarizations? So let's think about it. So we have the recordings. We usually split that recordings into a small set of segments. Usually it is done for the computational efficiency. Here, we assume that we split the recordings by silence. And important thing is that even we split the audio, each segment could consist of multiple speakers. Yes, we extract features from features. And let's call the entire feature as large X. So what is the target of speech recognition and speaker diarizations? Here, I assume, in this figure, I assume there are two speakers, speaker 1 and speaker 2. And red part represents the non-science hypothesis for speaker 1. And blue part represents the non-science hypothesis for speaker 2. And white part is the science hypothesis. So if we think the hypothesis, including the informations of non-science and science information, this is the target. This is the target of speech recognition and speaker diarization. We know what is said, and we also know when it is said, right? So what we want to solve is, given observation X, we want to estimate the most plausible recognition hypothesis W. It is a bit difficult to directly solve this problem. So I introduced one hidden variables as speaker embeddings. So this speaker embeddings represent the characteristics of speaker 1 or speaker 2. And the target problem can be extended by using these hidden variables. Firstly, we introduce the marginalization by speaker embeddings, and then we approximate this summation operation into max operations. So then we see that the joint problem of ASR and speaker diarization is the joint maximization problem of speaker embeddings and recognition hypothesis given observations. It is still difficult to directly solve this joint problem. So we propose iterative optimizations to solve this problem. So what we did is, firstly, we fix the word hypothesis and try to find the embeddings that maximize the joint probability. Then we fix the embeddings and try to find the hypothesis that maximize the joint probability. By iterating this procedure, we can monotonically increase the joint probability. So this is the idea of iterative optimizations. And find the embeddings that maximize the joint probability of word and embeddings is equivalent to find the embeddings that maximize the posterior of embeddings given W and X. So this is equivalent by applying the chain rule. So finally, we can decompose the problem of joint speech recognition and speaker diarization into two problems. One is find embeddings giving the hypothesis, and one is find hypothesis giving the speaker embeddings. Then the final thing that we need to do is the implementations. So what we can do to find the best embeddings given hypothesis. For this, firstly, we already have the hypothesis, including the science frames. And what we did at the time is that by using this information, we can know where is the single speaker region and where is the speaker overlap region. So we extract the speaker embeddings only by using the single speaker region given the hypothesis. This is what we did to estimate the good speaker embedding estimations. One thing that I need to mention is that at the very beginning of the procedure, we don't have any hypothesis. So we need to estimate the speaker embeddings without word hypothesis. For this, we just apply the conventional speaker diarization method. So this is how we estimate the speaker embeddings. And also, what is the meaning of estimating the hypothesis given speaker embeddings? Here, we can use Target-Speaker ASR. So we have the observation and we know the embeddings. So we can feed these embeddings into Target-Speaker ASR, and Target-Speaker ASR will produce the hypothesis with silence information. And we iterate this procedure. So this is what we did. We did experimentation with corpus of spontaneous Japanese. Most contents are lecture recordings by a single speaker. And we use this CSJ dataset as the training data for I-vector extractions and target speaker SR training. CSJ also contains some dialogue contents. So we use this 54 dialogues as a version dataset. This is dialogue. So this is two speakers speech. This two-speaker speech is recorded in soundproof chamber divided by a glass window like this. And these talks are recorded by headset. So we have a clean single channel audio for each speaker. For evaluation, we just mix this two-speaker speech. So in terms of timing of speaker time, it's superior. When we calculate the speaker overlap ratio, it's about 20%. In terms of noise or reversion, it's not real, but it's still a kind of real conversation. So firstly, we evaluate the oracle settings. We use the clean acoustic models, and we have the single speakers recording. So we evaluated the audio before mixing. So we got 90.93 word rate. So this is the this is the oracle word rate that we can get for this dataset. We also try to apply normal clean acoustic models for the two-speaker mixed speech, and the word rate is super bad, of course. Then we swap the clean acoustic models in target speaker acoustic models. By using target speaker acoustic models, we can get much better result compared with the normal acoustic models. We also, yeah.
Sorry to interrupt. There is a question. You want to answer it in the QA session, or you can answer it now. It's on the embeddings.
Okay, I can answer now.
Okay, so in the iterative estimation, it seems you are estimating speaker embeddings using only the segment boundaries and discarding the contents, words. What are your thoughts on using something like a language model to use content, also in the speaker embedding estimation?
Yeah, it's a good point. Right, and I am using the only word boundary, and yeah, we can think about it. At that time, we don't have a good idea to use that, but we can use it. Yes, it's very good. Thanks. And actually, I will talk about another models to combine the speaker estimations and word how to say to combine the word recognition and speaker identifications. So I need to explain a bit very faster, actually. Sorry. So anyway, I will continue my talks. So okay, so here I use target speaker acoustic models, and the difference between the third experiment and fourth experiment is that instead of using embeddings of E1 and E2, I just use embeddings of E1 and use the interference speaker ASR for the recognition. At that time, the result is not very good, but the experiment of 2, 3, 4 is, I forget to mention it, but for this experiment, I use the Oracle speaker embeddings by using the Oracle segmentation information. So finally, we try to use the estimated speaker embeddings as the initial target. So instead of using the Oracle speaker embeddings, we firstly apply the k-means-based speaker diarization and use the speaker center or to get the initial speaker embeddings. Then we apply the target speaker models. The result is significantly degraded compared with the Oracle speaker embeddings. In that situations, the using interference speaker ASR was a bit better compared with using the both E1 and E2. At that time, what we did is that we selected the cluster, bigger cluster compared with, sorry, we have the two clusters, and one cluster is bigger than other clusters. So we use the only big clusters to estimate the speaker embeddings or E1, and use that E1 as the target speaker embeddings and apply the target speaker SR. So we observe the significant improvement by this method. So we use this for the next experimentation. Finally,
before you go on, John has a question, John Hershey. He says,
okay.
are the in the probabilistic formulation, you treat the speaker embeddings as random variables, but does the model use a distribution of the embedding or only point estimates?
Only point estimate. Yeah, it's also a good point. I use only estimate, only point estimate. Yeah, in my experimentation. Okay.
And there's one more question. They say, what is the motivation for the assumption that P of E, I guess that's from the previous slide, E given WX is maximized by considering all the non-silence, non-overlap regions for a speaker, right? For a speaker.
Sorry, could you repeat the question?
You can look at the Q&A, but I'll repeat it again. What is the motivation for the assumption that P of E given WX is maximized by considering all the non-silence, non-overlap regions for a speaker? Do you think it would benefit if we use only high confidence regions or some definition of confidence, or for some definition of confidence?
Yeah. So yes, we can probably do that. This is please think about this is only one possible implementation that we can do. At that time, we assume that the mixed region is totally contaminated. So we cannot fully use these regions. And yes, we can use the probability, for example, confidence to weight the embeddings, and it will be better way. So I need to say this is a very rough approximation of what we want to do. Here, what I wanted to show is that we can think about the formulations in this way, and we can think the optimization problem in some theoretical way. But this is still approximation.
Thanks.
Yeah, thanks for your questions. Okay, so yeah, so I think I already show the core result. So by iterating the procedure, we got the over 10% of improvement. So this is the effect of joint optimization of speaker recognition and speaker diarization. And we may be able to improve it by what you suggested. So this is the diarization result. I will skip this slide, but basically I got a very good result by using the joint optimizations. Yeah. So so far, okay. So I passed one highlight, and I want to explain another direction of research. So what I show you in the combination of speech recognition and diarization is we use Target-Speaker ASR. And in the previous experimentations, I assume that we know the number of speakers is 2. So we actually we use the k-means with two clusters of k-means by giving the number of speakers. So what I wanted to do next is adding the ability of speaker counting into speech separation and ASR. So we looked for tools that can recognize words of any number of speakers. So can we use permutation invariant training? But we saw that, but there are limitations that in the permutation invariant training. Firstly, as I already mentioned, the number of output branch constrains the number of recognizable speakers. Also, there is another problem that each decoder works totally independently in permutation invariant training. And this could be a problem because this decoder works independently, it is possible that duplicated hypothesis is generated for these two branches. This is another possible problem, but because we treat each decoder independently, we cannot represent the dialogue level context between the first transcription and second transcription. Finally, as I already mentioned, it takes order of factorial of number of output of training cost. So I wanted to avoid these limitations, and I wanted to solve the multiple talker ASR with any number of speakers. So what we recently proposed is so-called serialized output training, in short, SALT. The idea is super simple. Instead of having multiple output branch, we concatenate the reference labels by using the special symbol. It is a speaker change symbol. We need to use attention encoder decoder type architecture because input is overall speech. So attention needs to firstly go over the first speakers and then go back to the second speakers and then transcribe the second speaker differences. So it is not possible for hybrid systems or RNA transducer, but for attention encoder decoder, it is actually possible. And decoder is run until end of sentence mark is estimated. So it is naturally including speaker counting problem inside. There are many good things for SALT. Firstly, we don't have any constraints in the number of speakers. This is a good thing. Also, we are treating the utterances in one sequence, so we can use the dependency among the first sentence and second sentence. The remaining thing is that how we can train this model. So one way is to calculate the all possible concatenations patterns and use the minimum loss among the possible hypotheses. This is the variant of permutation invariant training, and we call it minimum loss speaker order. Another way that we found very effective is instead of evaluating all possible combinations, we sort the reference labels in the order of start times. So in this example, second speaker start first and first speaker second next. In that case, second speaker transcriptions is put first and the first speaker transcription is put next. We call it first in, first out order training. Good thing of this is that only by giving the start time, we can train this model without considering any combinations. So the training is much faster. We did experimentation with LibriSpeech. We did simulations in this experimentation. So for training data, we set the minimum delay of 0.5 seconds and maximum duration of previously mixed speech. So in the maximum overlap case, the training data is like this, and minimum overlap case, the training data is like this. And we just randomly selected the delay when we generate the training data set. In case of testing, we remove the minimum delay. So minimum delay is 0.0 second. It means that multiple utterances could start at the same time in the evaluation dataset. So minimum delay is only set for training dataset. So what we firstly did is the experimentation with two-speaker mixed speech. We did relatively small models for these experimentations. If we use single-speaker ASR, And if we apply it to two speaker mix dev screen and test screen, of course, result is very bad. And fortunately, SALT works very well for this two speaker mix speech. The best thing that we found is that surprisingly, first in, first order, first out method works better than minimal speaker order. It is very good because this first in, first out training is much faster than minimal speaker order. So basically, we use this first in, first order training for the every experimentations. Next. We also evaluated with a variable number of speakers in training and testing. So here we prepare the evaluation data with single speaker, two speaker mix, or three speaker mix. And here is the result of single speaker ASR or SALT with two speaker training data, or the combination of single speaker and two speaker training data, or a combination of 1, 2, and 3. So when we use the combination of all possible combination of speaker mixtures, our SALT model produces surprisingly good result for this, even for this three speaker mixed case. One more thing that I wanted to one more thing that I want to emphasize here is that by using SALT, we got better result even for single speaker case. And we consistently observe this result when we use the SALT. And we think this is due to the data augmentation effect compared with a single speaker case. So we are mixing the trial data. So this have a kind of data augmentation. This is, I think, a really good property of SALT, because usually if we apply speech separation, we often observe the degradation for single speaker case. Yeah, so we try different model size, and what we found is, in short, the sufficient number of parameters were necessary to achieve good accuracy in SALT. So if you want to apply SALT, and I recommend you to use sufficient. I don't know what is a sufficient number, but at least you need to use relatively large number of parameters for trying. So due to the time, I would like to skip this slide. So we compare the SALT and PIT. We try the two output PIT with two speaker training data, or the combination of 1 and 2. If we compare the PIT, for example, if we see the two speaker mixture of evaluation data set here, SALT achieves a close number with PIT. And at the same time, SALT achieves very good number for single speaker case and three speaker case, even with a slightly less number of parameters. Again, I wanted to emphasize that SALT show any degradations in single speaker case. And I think this is very good. On the other hand, in PIT, we observe the degradations for single speaker case. This is speaker counting accuracy by SALT. I forgot to mention it, but previous my results all include the speaker counting errors into the consideration when we count the word rate. So SALT model produces any number of speakers hypothesis. So if we produce many speakers compared with the reference levels, we treat it as insertion error when we count the word rate. On the other hand, if we SALT model produces less number of hypotheses, we count it as a deletion error. So speaker counting accuracy is very important. If we look at the speaker counting accuracy, for example, in single speaker case, SALT model counts the number of speakers correctly as 1 in 99.8%. So it's very good. Even for two speaker case, it counts the number of speakers correctly as 90.7% of accuracy. But there is a remaining issue of SALT. In case of three speakers, it tends to count the number of speakers as 2. So it In short, it tends to underestimate the number of speakers, but it can still count the number of speakers correctly with around 75% of accuracy. Okay, so this is the short summary. We recently proposed JSALT. It has a very good property. We don't have any restriction for number of speakers that can be recognized, and it can be trained with order 1 complexity with respect to the number of speakers, and it can represent the dependency between multiple utterances. Okay, so this is the last topic that I prepared for today's presentations. I wanted to again combine speaker identifications. So in this case, I try to combine speaker identification instead of speaker diarization. So here is the slide that I used for the very beginning of my presentations. So what we want to do is the rich transcriptions and transcriptions of speakers, and at the same time we want to estimate the speaker identity. And in this work, we feed the speaker profiles that represent the speaker characteristics of participant. Our proposed method is we rethink the problem as a sequence-to-sequence transduction problem. So as we saw, we can represent the transcription as multiple speaker transcription as a sequence of words by joined with speaker change symbol. So we use it. And at the same time, we also want to estimate the speaker identity. So we also think the speaker identity for each token in this case. And speaker identity for the speaker change symbol or end of sentence symbol is used for is picked up from the previous utterance. What we did here is we first estimate one of the speakers to transcribe. Then, given that estimations, we estimate the word. Then we re-estimate the speakers, and then we estimate the word again. And we continue this procedure. So here is the dependency link of speaker and word and speaker and speaker and word, speaker and word. And we use this dependency to model the sequence-to-sequence problem. This can be formulated by as a Turing criterion. We call it speaker attributed maximum mutual information Turing. So X is observation, speech, and D is inventory, and Y is word sequence, and S is speaker sequence, and S is a token-based speaker symbol. We can decompose it into two parts, as I just show in the slide. So first thing what we want to do is estimate the speaker of nth token, giving the previous estimation of word and speakers. Then we estimate the token, nth token, given the previous estimation of word and previous estimation of speakers. And we can iterate it rigorously just by using the chain rule. So this is the idea of speaker attributed MMI learning. So the last thing is how we can represent this model. So I will explain the model architecture. So we start from the usual attention encoder decoder based speech recognition. So this is the usual speech recognition. Input is X over speech, and output is a sort type ASR result. We have ASR encoder, we have attentions, and we have decoder here. First thing that we introduce is we introduce speaker encoder. The motivation here is that we want to represent the speaker characteristics of overall speech. And we borrow the attention weight from ASR to make one weighted average of speaker embeddings. Important thing here is that we are tolerating overlap speech. So some frames could be contaminated by multiple speakers. So even after attention is applied, this PN is still contaminated by multiple speakers. So we introduce one more recurrent neural networks layer to purify the speaker characteristics. For this RNN, input is previous QN and previous word sequence, and the output is QN. And you can think that QN is the speaker embeddings, purified speaker embeddings, estimated from the overall speech. Then we can compare this QN with speaker inventory to find the best speaker, to find the best matched speakers to do the speaker identifications. Okay, so finally, what we did is we can get the average, weighted average of speaker inventory by using the speaker estimations, and we feed this average speaker inventory into decoders. Then we have the totally looped architectures to estimate the speaker identifications and speech recognition result simultaneously. So we did the evaluation with LibriSpeech, again, simulated mixtures. Here, when we apply single speaker ASR, and we have the single speaker ASR and SOT model. And evaluation data is single speaker model, two speaker model, and three speaker model. Again, single speaker ASR produced very bad result for mixed speech, but SOT model achieved good result for speaker agnostic word rate. Sorry, I didn't mention it, but we calculated the speaker error rate, speaker agnostic word rate without considering the speaker attributions, and speaker attribute word rate with considering the speaker attributions. So as the baseline, we combine the SOT and D vector-based speaker identifications. What we did here is that we are using SOT, so we have the attention weight. So we use that attention weight to get the average D vectors, and use that average D vector, and by comparing that average D vector with speaker inventory with cosine distance, we can find who is the speaker. And it actually works well, especially for single speaker case. Speaker error rate is only 0.4%, and speaker agnostic word rate and speaker attributed word rate is very close. But there are some degradation for mixed speaker case because we are using average, weighted average of the vectors, and it may be contaminated by the overall speech. Finally, this is the result with proposed method. We can see the improvement for most cases, just except the speaker agnostic word rate for three speaker mixed case. But speaker attribute word rate is significantly improved by using our method. So this is the result that we got by combining everything. We did some aberration test to check whether the component is really necessary. So if we use the PN, this is contaminated speaker characteristics, average word rate is 80.2. And by using speaker query RNN, we got the improvement to 16.7. And finally, by adding the weighted average of speaker identification result, we got further improvement to 15.6. Speaker counting accuracy is very close to the SOT case. So unfortunately, we don't observe a significant gain by combining this compared with SOT, but still, I think it's pretty good. So single speaker case or two speaker case, it can estimate the number of speakers very correctly. Finally, I would like to point out the difference to the target speaker ASR. So left-hand side is target speaker ASR. So if we want to apply target speaker ASR for many speakers, we need to apply target speaker ASR independently for each speaker profile. The thing is that if there are very similar speaker profiles, it is very possible that duplicated hypothesis is generated for each target speaker ASR. It will happen, especially if the number of speaker profiles are large. On the other hand, our method consumes speaker profiles directory and tries to estimate whole representation of output. So there is no difficulty to cope with many number of speaker profiles. So this is the fundamental difference between Target-Speaker ASR and our proposed end-to-end speaker attribute ASR. So to see that, we try to use 32 profiles for inventory, and the target is still 1 or 2 or 3 speakers. If we compare the inventory size of 4, 8, 16, 32, and you can see that the degradation of speaker error rate or speaker attribute water rate is marginal compared with the number of speaker inventory, a number of speaker profiles in inventory. So this is the power of using the end-to-end speaker attribute ASR that we propose. Okay, thank you. So this is the last slide that I prepared. So this is just summary, and I show how we can think about the joint modeling for rich transcriptions. One way is combining multiple modules into single model, as we see the last slide, speaker attribute water rate. And other thing is solving multiple problems towards joint optimization of one of the functions. And I am still on the way to solve the rich transcription problem. So I show some examples. I think that I show some examples for how we can think about the joint problem. So I hope that my presentation helps you think about the rich transcription, and we can get a good result for the problem. Thank you. Thank you for your attention.
Thank you, Naoyuki.
Thank you for the great talk.
Yeah.
So audience, the floor is open for questions. I already see one in the Q&A. At this point, I'm happy to turn on people's microphones so that they can ask the questions in person. I'll begin with Roshan. Roshan, I've turned on your mic. Please go ahead and ask your question orally if you like.
Thanks for the presentation. It was very interesting. So I had two clarifications about the serialized output training approach. So the first one is that when you talk about 1 speaker versus 1,2 speakers versus 1, 2, 3 speakers, the data augmentation is in the ratio 1:2:3, or is it the same amount of data that you use to train these models?
No. And for this particular experimentation, we use the actually 3 times larger training set for 1 and 2 and 3 case. But I didn't show that, but when I even use the larger training set for single speaker case, I didn't observe the gain. No, so sorry. And when I change the data size, it is impossible to increase the size of single speaker case. But when we change the size of training data set, we didn't observe the good improvement by that.
So another thing is that there's a significant difference between performance with overlapped and non-overlapped models, something like 5% versus 17%. So do you think that is because we are not modeling overlapped acoustics per speaker in the encoder, like something like PIT, wherein they have speaker dependent and speaker independent parameters that they train?
So sorry, and which point are you mentioning? So this one?
No, I think it's the previous slide maybe. So you pointed out that in the non-overlap model for test clean, dev clean, you get around 5.4.
Right.
But with overlapped speech, you get around 17.
Right.
My question is that possibly because you're not handling acoustics per speaker in the encoder, because you're not making any change to the encoder setup, right?
It is possible, especially if we use small number of parameters, it is really possible. So this is why I suggested you to use the sufficiently large number of parameters, especially encoder is very important for thought because it is necessary to represent the multiple speakers speech. Yes, exactly, yes. So actually, today I skip one slide for that experimentation. So in case of PIT, we separate the embeddings into 2 speakers. In case of 2 speakers, we separate represent the embeddings for each speaker in case of PID. But in case of SALT, we still use the single encoder, right? As you said. So it means that embedding is still contaminated by multiple speakers. So one thing that we propose is that instead of, so we can think that separation is done before attention in case of permutation by learning, but we don't have that separation modules inside the SALT. So what we propose is instead of having separation before attention, we insert one more nonlinear layer after attention layers. And it usually don't have any effect on the attention encoder decoder based ASR, especially if the training dataset is single speaker. But we observe the improvement by adding one more LSTM layer here. So this is the comparison between the two things. So finally, we got 11.2% value rate by combining all of these.
Thank you.
Yeah.
Thank you. There's a question from Shinji. Shinji, go ahead.
Okay, can you hear me?
Yeah.
Yes.
Okay, Naoyuki, thank you for your great talk.
Yeah, thanks.
I actually would like to know more about the analysis of the source target attention, what happened. For example, we have applied the target speaker end-to-end ASR with the people in NTT, we found that source target attention actually will clearly attend the target speaker region, and we can actually perform diarization based on the attention weight as well. So do you also observe some kind of a clear attention, source target attention pattern in your approach? We try to have this, each of the kind of the sentence, the token can kind of attend the correct position of the input frame, and you can also compute the diarization error rate from that. So do you have such kind of analysis?
I didn't do the, how to say, objective analysis. I saw that the attention weight is basically correctly pointed to the position of word, but I didn't do any kind of objective evaluation of that.
Yeah, I strongly recommend you to do some more analysis. I believe it can perform some level of the diarization through the attention weight. It's, the word error rate clearly shows that it can be done, but this kind of method have the potential of the visualizing or even having a side the effect of the providing good information. So I usually love the attention more than the other architecture because we can visualize or we can provide more meaning. So that is my recommendation. And another suggestion is, again, attention. We should also try the self-attention.
Yeah, right. Yeah, actually, there is no great reason that I didn't use transformers for this experimentation.
Yeah, I'm very happy to see such kind of extension as well. Again, transformer, we have a lot of attention parts, so we can have a lot of analysis. But the problem of the transformer is that so many source target attentions. So compared with the RNN, there's some kind of result are mixed. But it's quite interesting to see this kind of a source target attention visualization. Yeah, but you already checked it, but I think I strongly recommend to do it.
Yeah, thank you. Thank you for your suggestions.
Good comment, Shinji. Yeah. Well, there are a lot of distinguished people in the audience. If any of them have any comments, Hinek, I invite you if you feel like speaking up. And also John, Ivan Medenikov. I see Murat is in the audience. Amos, anyone? Ivan, let me allow you to speak. Go ahead, Ivan.
Hello, can you hear me?
Yes.
Yeah.
Yeah, thank you for a great talk. I have one question. Do you have any plans to evaluate your approach in more realistic data, for example, in CHIME6?
Yes, of course.
Let's do it.
Yeah, yeah. Internally, I am doing, and I need to think how I can present it. But yes, of course.
Yeah. Well, actually, inside the company, we actually has tons of the real data, right? But the publication sometimes is another thing, right?
Okay. Thank you very much.
Yeah, thanks.
So, do you have any comments or questions? Any reactions?
No. I mean, we actually have meetings every maybe twice a week, so I don't really have questions.
Yeah.
Okay, let me poll the audience again. One last round of questions. Anyone?
Thank you. Okay, let's thank.
Right, let's thank Naoyuki again.
Yeah, thank you so much. Thank you so much for your time.
All right, and let's call the seminar to a close. Again, reminder everybody, we'll have another talk on Friday at 10 o'clock.
Thank you.
Bye-bye.